Okay, in this section, we're going to talk about orthogonal sets. So 6.2 orthogonal sets. Now, a couple of definitions in this section are maybe a bit silly, maybe a bit self-evident, you might say. So 6.2 is called orthogonal sets. So our first definition is for an orthogonal set, and an orthogonal set is exactly what you expect it to be. It is a set of vectors that are orthogonal. Okay, and then parentheses to each other, just refreshing our definition that orthogonality is a relationship between vectors. Okay, so a set of vectors that are orthogonal to each other. Okay, that is an orthogonal set. So let's look at the set U1 equals 4, 1, negative 1. U2 is going to be equal to 1/2, 1, 3. And U3 be equal to 1, negative 2, and 2. Okay? Oh, let's look and see if these are orthogonal. Remember, to be orthogonal, you need the dot product to be 0. So I need to do U1 dot U2. U1 dot U2, I got 4 times 1/2, that's 2. 1 times 1, that's 1. 1 times negative 3 is minus 3. I get 0. Okay, it's a good start. Let's do U1 dot U3. So 4 times 1 is 4. 1 times a negative 2 is a negative 2. Negative 1 times 2 is a negative 2. 4 minus 2 is 0, so that's good. And then U2 dot U3. So I have 1/2 times 1, that's 1/2. 1 times negative 2, that's negative 2. And 3 times 2 is 6. So that is 4.5. That is 9/2. That is a problem, right? That is decidedly not 0. So my set, U1, U2, U3, is not orthogonal. Okay, so making the point here, just because you have a pair that's orthogonal is not enough. Every pair of vectors in the set has to be orthogonal. So if you've got 3 vectors, you've got 3 dot products to check. If you've got 4 vectors, you have 6 dot products to check. Now, if you just have 2 vectors, then you just have 1. So that's pretty easy setup. But if you got, if you got 5 vectors, you've got 10 dot products to check. Okay, so any set, you've got to make sure that they're all orthogonal to each other, not just a couple. Every pair has to be a dot product of 0 and not anything non-zero. Okay, so let's try another set. U1 here is going to be 1, negative 2, and 1. U2, let me just make the point that's why that wasn't 0. Sorry, I had that in my notes and didn't write it down. 0, 1, and 2. I said it instead of drawing my arrow. All right, so then I finished my second set here with negative 5, negative 2, and 1. Okay, and we're going to check those dot products. So U1 dot U2, 1 times 0 is 0. Negative 2 times 1 is negative 2. And 2 times 1 is 2, and that is 0. So that's good. Let's do U1 dot U3. Okay. So 1 times negative 5 is a negative 5. Negative 2 times negative 2 is a positive 4. And 1 times 1 is a positive 1. So that's 0 again. And then I got to do U2 dot U3. That's where I got hung up last time. 0 times negative 5 is 0. 1 times a negative 2 is a negative 2. And 2 times 1 is a positive 2. I get 0. So U1, U2, U3. Notice it's in braces. So this is the set of vectors. Okay, these are all vectors. All right, there's not a good way to bold them in handwriting, but you can always tell the difference in text. Set of vectors, and this set of vectors is orthogonal. Okay, so we're going to talk about a couple of properties for orthogonal sets or orthogonality. Okay, so if I have an orthogonal basis, so remember what an orthogonal basis was. It was a set that all the vectors are orthogonal. Okay, orthogonal basis was a basis for a space. So an orthogonal basis for subspace W that's a subset of Rn, so W is in Rn, is naturally a basis. So remember what it means to be a basis. The vectors are linearly independent, and they span all of W in this case, okay? Linearly independent and spans, okay? So it's a basis that is an orthogonal set. So again, another kind of silly definition, okay, naturally. And so think about what this means. It's a basis. If it's a basis, it's linearly independent, okay? So the implications there are significant, right? So if you have a set U1 to UP, so I have P vectors here, U1 through UP, that are orthogonal okay? So U1 through UP are orthogonal. And linearly independent. Then we have Y is equal to a linear combination. Okay, remember that these are still vectors. They're linearly independent vectors, so that means I could write them. This is U2 and this is CP UP. Okay, they're linearly independent, so I can always write Y is equal to some linear combination of weights here. And if Y equals 0, the equation has only the trivial solution. Okay, we know that because of linear independence. Okay, if you have linear independence, you know you have only the trivial solution. Okay, all right, so we can be even better than that. Okay, so certainly if I have linear independence, I have only the trivial solution. Okay, but what if I don't know they're linearly independent? Okay, so for our theorem 4 here, so in theorem 4, which I'm going to actually write the theorem down on the next page, but it's what we're talking about. Theorem 4 here, we're going to look at what if I don't know linear independence? Okay, what if I strike that? Okay, let me take red here. Okay, so now for theorem 4, I'm going to strike that it's linearly independent. So let's look at the implications here. So I have 0 is equal to C1 U1 plus C2 U2 plus CP UP. Oh, forgot my dots. Sorry, dots in the middle. Using that same equation I just had. Okay. I don't know that these are all 0 now. I don't know that it has just the trivial solution. Okay. But I do know they're orthogonal. So I'm going to take 0. I'm going to take both sides of this equation and do a dot product on the left with U1. And ultimately, I could pick any of my vectors. I just picked U1 simply because it was first. Okay. This is an equation. This is an equation of numbers. So I know that simply doing that operation with the dot product on the right on both sides of the equation will still maintain an equation. Well, I know 0 dotted with anything is 0. Okay, I know that. The 0 vector. All right, this is the 0 vector. Okay, so I definitely have 0 on that side. I know I have distribution here of this. So I'm going to have C1 times U1 dot U1, C2 times U2 dot U1, an ellipse. I have all the ones in the middle, and then I'm going to end with CP times UP dot UP. Okay, go back and check your property. I'm sorry, not UP dot UP, UP dot U1. Go back and check your properties of dot products. Remember, we can do distribution here. So I stuck each of these with that, and I could separate out the scalar. Okay, but the vectors are orthogonal to each other. So u2 dot u2 has to be 0. up dot u1 has to be 0. All the ones in the middle have to be 0. So I'm left with c1 equal to u1 dot u1. Okay, I kill off all those terms. And now u1 dot u1 can't be 0. Again, check those properties for dot products, right? Remember, something dot product with itself has to be positive, greater than or equal to 0, and it can only be 0 if the vector itself is the 0 vector. So I don't have the 0 vector here because it's linearly, I don't know that it's linearly independent, okay? So either u1 dot u1 is 0 or c1 is 0, okay? So either u1 dot u1 is 0 or c1 is 0. And if c1 is 0, I have only the trivial solution. Okay, if u1 dot u1 is 0, then I definitely don't have an independent set because any set containing the 0 vector is going to be dependent. Okay, so what we have there in theorem 4 then is that any orthogonal set that is also a basis, okay, I'm sorry, any orthogonal set that's independent is also a basis. Okay, because if it's 0 vector, it's not independent. Right? And if it's not the 0 vector, then they're clearly independent. And if you have p vectors that are independent, you know you have a basis. So the text of theorem 4 then, so we'll write down theorem 4 officially. Okay, it's just setting up what we're getting, okay, because it's not an accident. I know sometimes it can feel that way when you write down theorems that we say, okay, a miracle occurs and we have this theorem. But that's not the case. We can see that it follows from the properties. So if I have a set that's u1 through up is an orthogonal set, u1 through up is an orthogonal set of non-zero. So notice I did have to add that caveat. I didn't have that before in my setup properties. I do have to add that it's a non-zero vector because 0 vector is orthogonal to everything. Okay, because the dot product with 0 is going to be 0. So non-zero vectors in Rn then S, which is my set, is linearly independent and thus is a basis for the set spanned by S. So if S happens to be the entire, if the spanning set here, the spanned set happens to be all of Rn or R2 or Rp in this case, then it covers the whole set. It doesn't have to be the whole space, I should say, but at least the whole area, the whole plane or hyperplane, whatever geometric representation you have for that, okay? All right, and so we defined a orthonormal set, or orthogonal set, I should say. We defined an orthogonal basis, okay? That's simply a basis that's an orthogonal set. And what we see here is that if I have linear independence and orthogonality, I get a basis, okay? So simply put theorem 4, linear independence plus orthogonality linear, I wrote that backwards. Scratch that. Orthogonality, sorry, get those backwards in order. Orthogonality is going to give us linear independence. And linear independence gets us a basis, okay? But it's a basis for only what's covered by the vectors in S, okay? All right, next up. We want to look at, can I use dot products to find what those weights are? You know, we know how to find a system of equations, right? We've done that. We augment our vectors, right? This would be U1 through UP. We have our unknowns B1 through BP, and we solve that system, and hopefully we get the identity here, with my vector B, or my weights X1 through sorry, let me get that right. X1 through XP, my weights, or C1 through CP, whatever it might be. Hopefully I get my vector set up there with independence. Okay. All right. We don't want to do that every time if we can help it. And the dot product process is fairly easy. Okay, so if I consider that equation that I had before, just the linear independence equation, right? U1 through UP. Okay. Well, I know I can take a dot product, so pick your favorite one to do the dot product by. Let's say CJ. Okay. Well, when I do this dot product, just like my last proof, they're all going to go to 0, except for the one that has the same vector. So uj dot uj will be left over. So if I'm looking for this, sorry, I don't want to multiply it by, dot it by CJ. I want to dot it by uj. There we go. I'm doing dot products, so they should be a vector. That looks better. Okay. Oh, uj, right? That's why I have uj and uj in the parenthesis. So if I'm looking for CJ, I can simply divide. Remember, uj dot uj is just a number. So CJ is going to be equal to y dot uj divided by uj dot uj. Okay, and that's for any j. J goes from 1 all the way out to p, because you have your set of vectors here, u1 through up. Okay, so we're going to have theorem 5 then is what reflects this. Okay, theorem 5 says you have u1 through up, an orthogonal basis, for W that's inside of Rn, for each Y in W, the weights in the linear combination so that's Y is equal to C1 dot U1 plus C2 dot U2 all the way out to CP dot UP. So the weights are CJ is equal to Y dot UJ divided by UJ dot UJ. Okay. So I'm going to take a orthogonal basis here. Okay, so I've got my orthogonal basis. U1 is equal to 1, 0, 1. U2 is going to be equal to -1, 4, and 1. And U3 is going to be equal to 2, 1, and -2. Okay. Now, I'm going to tell you that this is an orthogonal basis. Okay. You can always check it, right? 1 times 1 is -1. 0 plus 1, that's 0. 2, 0, and -2 makes 0 again. -2, 4, and -2 makes 0 again. So each pair here is orthogonal. So all the dot products are 0, so the whole thing's orthogonal. And my vector x that I'm interested in is going to be 8, -4, -3. So we are trying to write then C1 U1 plus C2 U2 plus C3 U3 is equal to X. Okay, and to do that, we're going to use this setup. So Cj is equal to y dot uj, which in this case it's x dot uj, which in this is going to be C1 and U1 dot U1 on the bottom. Okay, so on top, U1 dot x is 8, 0, and negative 3. That makes 5. On the bottom, I've got U1 dot U1. That's 1, 0, and 1. So that's 2. So C1 is 5 halves. Okay, C2 is going to be x dot U2 divided by U2 dot U2. So I've got negative 8, negative 4, and negative 3. Negative 8, negative 4, negative 3, that's negative 15. Divided by, inside here, I've got 1, 16, and 1. That's 18, which reduces to negative 5 over 6. You can put the negative out front, you can put the negative down 6, as long as only one of them is negative. Negative 5/6, okay? And then C3 will be x dot U3 divided by U3 dot U3. So I've got 8 times 2 is 16, negative 4, and positive 6. So 16 and negative 4 is 12, plus 6 is 18. I got 18 at the top. On bottom, U3 dot U3, I've got 4, 1, and 4 makes 9. 18 divided by 9 is 2. So then I could write the equation for x. X is equal to 5 halves U1 minus 5/6 U2 plus 2 U3. So there is my dependence relation. Okay, good to go. So all you have to do is compute each of these to find the relationship for that vector, assuming you've got an orthogonal basis for your original space. Okay? Well, you can do that with a 3 by 3. You can do that with a 2 by 2. You can do that with 4 by 1. You can do that if you only have 3 orthogonal vectors. Okay? Now, some matrices may be difficult to do RREF of. Some matrices may be easier. Okay? So what we're going to look at next is a bit of a visual. Okay? Well, if I take a space here, and I'm going to put 2 vectors in it, my vector y and my vector u. Okay? Now what I want to notice is y is clearly not orthogonal. It's not perpendicular to u. But if I extend u, okay, so I think of the span of u here, I can imagine extending y as well. And somewhere along here, I'm going to be able to take this vector and project it down to make a right angle. Okay, so there's some vector z here that if I project it down, I'm going to get a right angle. Okay, so the idea here is that I can take a vector y and turn it into 2 vectors, y perp or y hat. Okay, so that little caret symbol, hat, y hat is how we would usually say that, plus a vector that we will call z. Okay, and your observation should be that y and z, or I'm sorry, y hat and z are going to be orthogonal. Okay, y hat and z are orthogonal because y hat is going to be this piece where I've projected it. Okay, so I'm imagining, think of the shadow this vector casts on this line. Okay, this shadow shoots straight down here and makes a right angle. So this vector is z going across here, and this piece of u, so notice this u here, y hat's going to lie on that same line as u. Okay, so y hat is called the orthogonal projection. So it's the projection of y, so PROJ, projection of y onto the vector u. Okay, now you will also see this written as y hat projected onto the line L. Okay, and so the line L is simply the span of u. Okay, this gets us all of u. Okay, I think The nomenclature of projected onto U makes a little more sense, so that's what I tend to write, okay? But Y is projected onto U, so that is Y hat, okay? Now notice here, if you know Y hat, you can find Z by simply doing Y minus Y hat. Okay, I can just subtract Y hat over to the other side. Okay, so I can find both vectors that would be orthogonal to each other. So we could think of this as the orthogonal part, and this is the remaining part. Okay, this is the orthogonal projection, and Z is going to be orthogonal to the orthogonal projection. So it's that gap here. Okay, if a question asks you about distance, well, that tells you that you need to find the distance using the formulas from 6.1. Okay, distance was a 6.1 concept. Okay, so if I have a vector y, my vector y is going to be 1, -1. And I'm projecting this vector onto a u vector equal to -1, 3. Okay? So I'm going to take y hat then is going to be equal to the projection of u onto y. Now you'll notice I've not said what that projection is. Okay? So that projection, it's going to turn out, is exactly what we found for the linear combination, because I'm just putting it on this one combination vector. So my projection is going to be y dot u divided by u dot u times the vector u. Right? And my pen got a little sideways there. So y dot u times u dot u times the vector u. I'll write it again down here. Y dot u on top, u dot u, notice that is just a number. Okay, a number divided by a number is a number, and then times the vector u, because it should be a linear combination of u. So this is just the weight in the one vector set. So the one vector is, of course, linear independent because it's not the zero vector. So that's what we will have. Okay, so y hat, okay, is equal to the projection of y onto u, which for this vector will be y dot u. So 1 times -1 is -1. -1 times 3 is a -4. Divide that in the denominator, u dot u, that's 1, and 3 squared is 9. So 1 and 9 makes 10. And then I'm multiplying that times the vector u, which is -1, 3. So this is 2/5. So my new vector is -2/5. I'm sorry, +2/5. Get rid of that negative sign. But then I'm going to have a -6/5 on the bottom. So 2/5, -6/5. Now, if I need to find the vector z, what I do is I take y, which was 1 and -1, and I'm going to subtract the vector z, the vector y hat, I mean, 2/5 and -6/5. Okay, so 1 minus 2/5, that is 3/5. -1 plus 6/5, that is 1/5. Okay, so 3/5, 1/5. And now if you look at this, if I do y hat dot z, I'm going to get 3/5 times 2/5, that is 6/25, minus 6/25, because 1 times 6 is 6, and 5 times 5 is still 25. And that would be 0. So notice that y hat and z are orthogonal, just like we wanted them to be. Okay? So that is an orthogonal projection. Okay? You can write them as the sum of two vectors. So y hat is the orthogonal projection. Z is the vector that's orthogonal to y hat. Okay? So when it talks about writing a y as a sum of a vector in span U and or vector orthogonal, that's what you are doing. Okay? So orthogonal projection, just the y hat part. Okay? In this question, I'll write out the full text of the question so that we're clear. We're going to have y is equal to 2, 3, and u is going to be equal to 4, -7. And our job is going to be to write y as the sum of two orthogonal vectors one in span U and the other orthogonal to u. Now, the important thing to notice, if you're orthogonal to something in the span of u, you're orthogonal to u. Okay, multiplying by a constant is not going to change that relationship because you're going to multiply every coordinate by that same constant. Okay, so what we're asked to do here is the one in the span of u, this is y hat, and the one that's orthogonal to it is z. Okay, so I'm going to find y hat, which is equal to the projection of y onto u. So for that, I do y dot u. So 2 times 4 is 8, minus 21. That's a negative 21, negative 13. 8 minus 21 is a negative 13. And then u dot u on the bottom, I've got 16 and 49. So 16 and 49 makes 65. Okay, so that is a negative 1/4. Okay, and this should be times u. So when I multiply 1/4 times u, I'm going to have negative 1/4 times the vector 4, negative 7. So that's going to be negative 1/4 times 4. That's a negative 1. And then negative 1/4 times 7, that's a positive 7/4. So there's my vector y hat. So now to find z, I simply do y minus y hat. So y is 2, 3. And we're going to subtract y hat, which is negative 1 and 7/4. So 2 plus 1, that's 3. 3 minus 7/4, well, 3 is 12/4. So 12 minus 7/4 is 5/4. Okay. And now you can check that these are orthogonal. So I've got negative 3. And here I'm going to have okay, so I get negative 3, and I see that doesn't add up. So I got a multiplication mistake here. Actually, it was a division mistake. I'll do one more example just to clean this up. So that should be 1/5, right? 13 over 65 is 1/5. So that's going to actually turn this into 1/5 times this. So I'm going to get negative 4/5 for the first one. Now I still get 7, but it's over 5 now, 7/5 there. Okay, so let's clean that up. 7/5 and then negative 4/5 for the first one. So that's not going to be that. We're going to have 2 minus, be 2 plus 4/5. So that's going to be 14/5. And then my second one, 3 minus 7/5, that's 8/5. Okay. So that's negative 56/5 over 56 minus plus 56/5. So those we see are orthogonal to one another as well. Okay. So let's do one more of this type. Let's start wrapping up this section here. Okay, so the next one, I'm going to have 2 vectors here, same setup of the question. So I've got u is equal to 2, 6. Y is equal to, I wrote those backwards. Let's try that again. Y is equal to 2, 6, and u is equal to 7, 1. Okay, y 2, 6, 7, 1 there for u. So we're going to do the same thing. I'm looking for y is equal to a y hat plus a z, and we're trying to find y hat and z, and they should be orthogonal to one another. Okay, so y hat is equal to the projection of y onto u, which is going to be y dot u divided by u dot u times the vector u, which for us will be 14 and 6 is going to make 20 over u dot u is 50 times u. So I've got 2/5 times the vector 7, 1. So I'm going to get 14/5 and 2/5. Okay. Then to find the vector z, we're going to take y, which is 2, 6. Now we're going to subtract my vector I just found, 14/5 over 2/5. Okay, both positive there. So 2 minus 14/5 gets me a negative 4/5, because that's 10/5 minus 14/5. And 2 minus 6/5, or I'm sorry, 6 minus 2/5, I said that backwards. A little dyslexia for a moment. 6 minus 2/5, so 30 over 5 minus 2, that's going to be 28 over 5, 30 minus 2. Okay, so you got to be careful to keep all your numbers straight. You saw me make a mistake there. 20 over 50 is 2/5, it's not 1/4, or 13 over 65 is a fifth, not a fourth. So just be careful. There's a lot of arithmetic computations in there where you can make a mistake, okay? So just use caution as you are working your way through, okay? Now, for our last part of this section, okay, we've had a couple of silly definitions, and we're going to have one more. So you can probably guess once I write it down. So we're going to have an orthonormal basis. So to be orthonormal, that means it's an orthogonal basis. Orthogonal basis. They're all orthogonal to each other with unit vectors. Okay, and we know we can turn vectors into a unit vector by simply dividing them by their norm. Okay, so if I have 3 vectors here, u1 is going to be 3, 1, 1. u2 is going to be -1, 2, 1. And u3 is going to be -1, -4, and 7. Okay, so you could go through here and make sure that these are orthogonal, right? I've got -3, 2, and 1 is going to make 0. -3, -4, and 7 makes 0. u2 and u3, then I've got 1, -8, and 7 also makes 0. So this is an orthogonal basis, okay? So to find an orthonormal basis, I merely need to take u1 and divide it by its norm. Okay, and u2 and divide it by its norm, because we know dividing by a constant does not affect the linear independence or the orthogonality, either one. So to find an orthonormal basis, I merely divide by the norm. Okay, so remember what the norm of u1 would be. The norm of u1 would be u1 dot u1 under a square root. So u1 dot u1, this is 3 squared is 9. 1 squared is 1, and 1, so I get the square root of 11. Okay, that is the norm of u1. u2 dot u2 under a square root. I've got 1, 4, and 1. So I get the square root of 6. That's the norm of u2. And then the norm of u3, u3 dot u3. Okay, I've got 1, 16, and 49. That is the square root of 66. So that is the norm of u3. So now I can write an orthonormal basis. Okay, my orthonormal basis is going to be v1. Okay, that is the first vector, in this case 3 divided by the square root of 11, 1 divided by the square root of 11, and 1 divided by the square root of 11. I just took u1 and divided it by the norm that I found. v2 for my orthonormal basis. Okay, that's going to be -1 divided by the square root of 6, 2 divided by the square root of 6, and 1 divided by the square root of 6. And then v3, I am going to have -1 divided by the square root of 66, -4 divided by the square root of 66, and 7 divided by the square root of 66. Okay. Now, in general, I am fine with not rationalizing denominators, simplifying, that type of thing. Sometimes my math lab may care. Okay, so be mindful of what it asks for, simplified or not. In general, it does not care about rationalizing a denominator. It is fine with a radical in the denominator. But do pay attention to if simplifying can happen when you're looking at the My Math Lab homework. I, in general, do not care, especially for these kinds of vectors. Okay, so there's my orthonormal basis, v1, v2, and v3. Okay, so if you have an orthogonal basis, the way you get it to orthonormal is you simply divide by the norm. Okay, we're going to work a little more with projections, okay, and orthonormal and orthogonal and orthonormal basis in 6.3. And then we'll look at 6.4, an important factorization technique involving what's called the Graham-Schmidt process. Those are our last 2 sections for the semester. Okay, so I'll see you for those videos. Please contact me if I can be of any help. Come by office hours, send me an email, so forth. Happy to assist you. But I can't help you if I don't know what you need. Talk to you soon.